So this question is coming from Sapling. It's round number 28. Now, right? This is not necessarily going to be on the quiz tomorrow. Right? It's not going to be on the quiz tomorrow, right? The quiz is all up to everything we've talked about in class, right? So I'll still do it now. I'll do it quick, right?
Okay.
So it's basically the question is asking us, what's the difference between Lewis acid and Lewis base, right? So this is actually good. Some of the stuff is good for the quiz tomorrow. So it helps us. We got to remember, what do we define a base as? In terms of electrons, what does a base have? Is it electron rich or electron deficient? Electron rich. Good. And an acid, is it electron rich or electron deficient? Electron deficient. Deficient. Not a good speller. So in this case, you have something like this. FeCl4 with a minus plus so if you knew nothing else, whatever chemistry is going on here, if you know which one's electron rich and electron poor, you can identify the acid and base. In these cases, they call them Lewis acids and Lewis bases. Right? So the first part, so the second side is probably easier to see, right? On the product side, I guess. Right? You'd obviously say the FeCl4 is going to be the base, right? And the carbon with the plus charge here is probably going to be the acid. Now, what about the other side? What if I hadn't shown you, right? What if I hadn't shown you this? Had not shown you this? What if I just had shown you these two things? Could you still figure it out? You could, right? It's all about where the electrons are, where they want to be. So let's say you look at this ketone, this acetyl bond O, this carbonyl, and you're like, I don't know if that's electron rich or electron poor, right? Maybe that's not clear. Iron. Iron's what? Where is it at in the periodic table? It's in the middle. And what is iron? It's a metal. What do you guys know about metals? Are metals electron rich or are they electron poor? If you don't know, now you know that they are electron poor. Metals are electron deficient, right? They're electron deficient, right? They're not very electron rich. Those transition metals, they get some weird stuff going on. All that stuff in the middle of the periodic table, those are all electron deficient, right? That's why iron has oxidation states. So that's why iron's, right? You could also look at it and say, well, this iron's bonded to 3 chlorines, right? Those chlorines are pulling away all that electron density, right? So that means the iron's electron deficient. That means the iron's going to be the acid. And then by comparison, the other thing has to be the base. Where do you think that ketone is electron rich at? If you had to guess. The oxygen. What specific part of the oxygen? The electrons, right? I didn't draw them in, but are there lone pairs here? Yes. Absolutely, and those are the electron rich parts. Right? So that's really the basic, Lewis basic part here. But that still comes into, right, we talked a lot about acids and bases, electron rich, electron deficient. It's just applying that idea to a different thing than we've seen before. But it's the same idea, right? Who has the electrons? Who wants the electrons? That's all there is to it. Chemistry in general. So we're going to talk about bond angles and where they come from, right? So this is the way we presented this was, right, a series of facts, right? We ran some experiments, we found out the bond angles. We ran some experiments, we found out the bond strengths. And then we had to go back in time and explain in theory with these orbitals and these hybridization states to make that make sense in a model, right? So something we know. We know that this CH4, right, has what types of bonds? So what types of bonds does it have? How many of them? It has 4 sigma bonds. Right? Has 4 sigma bonds. We know the bond angle is 109.5. We know something about the bond length, right? We know something about it. Let's say it's longer. Let's say the bond strength, we can say the bond strength is 95 kilocals per mole. Right, that's just the energy. That's the bond strength, right? What else do we know about this? Let's stay with that for right now, right? We also know another example. We know something about a molecule like this. Right? And also be sure to note, right, we're talking about this carbon when we talk about hybridization. So for this molecule, what kind of bonds does this, what kind of bonds does this carbon have? It has 2 sigma bonds and 2 pi bonds. Good. What's the bond angle from here to here? 180. Do you guys know where we got that from? Where we can, so we actually can get crystal structures, right? Crystal structures, see a crystal structure of a molecule and actually measure the bond angles. Right? We can actually look at the molecule and measure the bond angle, right? With diffraction. That's how they did the double helix. That's how they figured out it was double helix, right? X-ray crystallography. You can even take a picture now of molecules and see. It's really cool. Well, I'll save it for later, right? So, know the bond angle. What else do we know? We know something about this bond strength. This bond strength is actually pretty strong. It's stronger than that. Let's say that bond strength is 110 kilocals per mole. All right? So that bond's a little stronger. What does that say about the bond length? The bond length going to be longer or shorter? Shorter, which must mean there's more orbital overlap too, right? They're sharing electrons better, more efficiently. Right? So now, all right, okay, let's do the intermediate one, shall we? Why not? We're here. Now, what about this carbon? What kind of bonds does that carbon have? This one has 3 sigma bonds and 1 pi bond. What's the bond angle from here to here? 120. Right? Right? But don't forget, there's also another bond angle in there too, right? This p orbital is coming out of the plane at us, and it's, right? The geometry, I didn't write the geometry, so maybe we'll go back and look at the geometries in a second. Right? Bond angle is 120. What about the bond strength here? What do you think it's going to be? If this guy was 95, this is 110. 100, 102, sure. These are all made up numbers, so don't quote me on this. 102 kcals per mole. So we calculated that. We know that bond's a little weaker than the triple bond version, but it's a little stronger than this version. Right, so those are all facts we know. So now we got to go back and say, well, okay, how are we going to make sense of where the electrons are at to make sense of these bond angles, the types of bonds, and the bond strengths? Right? So one thing we know for a fact is this triple bond, right, is we have these pi bonds. And pi bonds only come from what types of orbitals? All pi bonds have what types of molecular orbitals? P orbitals. So for every pi bond, you must have a p orbital. Whatever's left over gets mixed up and hybridized. Right? So for this case, we call this element, right, sp hybridized. That's its hybrid state. What kind of orbitals go with that hybrid state? Well, we have 2 pi bonds, so what 2 orbitals must we have? We'd have 2 p orbitals. And what's left over? We have to mix up the leftovers, and they're going to give us 2 SPs. Good. And of course, P's look like this. And SPs, they're 50% S, 50% P, right? So they're pretty fat and round still, right? So let's I draw them over exaggerated like this. Right? But that's good, right? We had to make them fat and round, right? That's why I made them this way, because what do we know about this CH bond? What do we know about that CH bond? Is it strong or weak? So we need this orbital to be more like an S shape, right? More spherical, because there would be better orbital overlap with an H here, right? And it's going to be a shorter bond too, right? So we need this orbital to be kind of shorter, right? What about for this carbon? What's its hybrid state? sp2. How many pi bonds does it have? So it has to have how many p orbitals? 1. So there's a p orbital. So what's left over? We have to hybridize to form those 3 sigma bonds. So what do we have left over? 3 sp2 orbitals. P orbital, the shape doesn't change, right? The p orbital is a p orbital. But now an sp2 orbital has 33% s, 66% p. So is it going to be short and fat, or just a little bit taller? A little bit taller. Why does it have to be? It has to be a little bit taller, a little bit longer, because what do we know about this bond strength? It isn't as strong, so that bond has to be longer, right? So we had to make up this orbital to make sense of this bond strength. It's a chicken and the egg argument here, right? At some level, this is all our own chemistry construct, right? But we can apply it and it works out most of the time, right? So what's left over for the last one? So for the last one, we have, what's the hybrid state of this carbon? It's sp3, we call it. That's the sp3 hybrid state. Does it have any pi bonds? So then does it have any unhybridized p orbitals? So it took the s and the 3 p's from a normal carbon and mixed them all up together. And what do we end up with? 4 sp3 orbitals. Right? Now these are going to be even a little longer yet, because the bond strength again, right, is a little bit weaker. Okay. So they're a little longer yet. Questions on this? So where we get this from this is where we get it from. Based on the data that we can get, we have to go back and make a model that makes sense. Okay, so let's draw out some geometry. So for this, I already kind of had it drawn out. And the bond angles come because, do electrons want to be next to each other? No, they want to get as far away from each other as possible, right, in these bonds. So this geometry, you can already see this geometry for this sp3 hybrid carbon, right, is tetrahedral. That's the best way we can do to get electrons as far from each other as possible. Right? But once you start throwing pi bonds in the mix, it's not as easy to get things away from each other. So let's take a look at this example, little ethylene. So the carbon here, right, we have a pi bond. Right, so I'll draw the pi bond in black. So you see the pi bond there? That accounts for one of the bonds of an sp2 hybridized carbon. I'm going to draw the sp2 orbital there. Right, and the other sp2 orbital, right, there. And there's an H, and there's an H, right? Because this bond right here has a pi bond and it has a sigma bond. Right? The p orbital is making the pi bond, and in sp2, sp2 and sp2 orbitals are making the sigma bonds. So there's a sigma bond to hydrogen, and then another sigma bond to carbon. That's what those orbitals are being used for. Right? So on this side we'll talk about that second bond angle. So these are just H's. So you guys know the bond angle from between the two H's is what? 120. But what's the bond angle from one of these H's to that p orbital, that pi bond? 90. Right? So that's something to think about. It matters, right? When we try to think about whether carbon wants to be, when it has a plus charge or a minus charge or as a radical, that second 90-degree bond angle comes into play, remember? We'll talk about that. So let's do the last one. Let's do the alkyne, triple bond. Right? So I'll draw the carbon. I'll draw one p orbital in black, forming the first pi bond. Right? The second pi bond, remember, is perpendicular to the first. Right? And then finally I'll draw in the fat old sp2s, or sp orbitals, excuse me, sp orbitals. Okay? And one of them is bonded to hydrogen here. Right? So we have pi bond with a p orbital, another pi bond, the p orbital, an sp orbital forming the sigma bond to H, another sp orbital forming a sigma bond to the other carbon. What about bond angles here? What's the bond angle from pi bond to pi bond, or p orbital, p orbital? What's the bond angle? 90. Good. Oop. Right. The bond angle that we all know about from here to here is what? 180, right? It's linear. I didn't draw those in, right? So this is a linear molecule. We call that linear. And the one up top we call trigonal planar. Good. So the question now is, if we got something like this, a carbon with a plus charge, not a full octet, call this a carbocation. Carbocation. Right? We have to figure out its geometry, right? Because that knowing its geometry, knowing its hybrid state is going to be really important for understanding how and why it reacts. Actually, super important, right? It's going to be really important, right? So we basically got to figure this out. So we can kind of eliminate sp hybrid states because, right? There's certainly not. Are there any pi bonds in CH3 plus? No, but we know for sure there's not two things, right? So we can kind of eliminate sp hybrid state. So we're kind of stuck with two options. We're stuck with either making it sp hybrid, sp2 hybrid, right? We can say it's sp2. And if something is sp2 hybridized, what molecular orbitals must it have? If you're sp2 hybridized, what are your molecular orbitals? You have one p orbital and then 3 sp2. So that's the kind of stuff you should be able to just spit out. All right? That should be intuitive to you. So if I'm going to draw this carbocation, this CH3 plus in the sp2 hybrid form, what would that look like? Well, that will look like this. Bless you. And I left the p orbital empty, right? So this sp2 orbital is helping bond to hydrogen. This one's also bonding to hydrogen. This one's also bonding to hydrogen. So what I have left over is this p orbital, and I left it empty. So there's no electrons in there. All right? We could also draw it in another conformation, which would be sp3. right? A little different. Let's draw a demarcation line here. Right? sp3 hybridized elements. If you're sp3 hybridized, what are your hybrid orbitals? 4 sp3s. sp3, 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 and sp3, right? Those are the hybrid orbitals for that hybridization state. So in this case, what type of orbital is empty? sp3 is empty, right? Because this sp3 is for this binding to hydrogen, this one's binding to hydrogen, this one's binding to hydrogen, this one's left over, well, it has to be empty. All right? So there are pictures. All right? So understanding this geometry is going to inform us on how this carbocation wants to be in three-dimensional space, right? How it wants to be. So what are some logical reasons one might be better than others? So the first rule of organic chemistry, of course, is electrons want to be apart, so like things repel each other, or opposites attract. So there's two different ways we can look at this. Right? There's two different ways we can look at this, right? So in Professor Ross's class, he explained it such that in bonds, oh no, there you go. In bonds, do bonds want to be as close, right, what's in a bond? What's in a bond? How many? Two. Still got it, yes. Do those electrons in those bonds want to be close to other bonds? Absolutely not. So they want to be as far away from each other as possible, right? Which one of these models gets the electrons as far away from each other as possible? Right. The electrons in the bonds. Right? This bond angle here is what? 120. What's the bond angle here in this sp3 hybrid? 109.5. Right? So that got the electrons in those bonds as far away from each other as possible. That's good. Like things repel each other. Let's be sp2 hybridized. Makes sense. That's one way to look at it. That's an acceptable answer. What's the other way to look at it? The other way to look at it is opposites attract. Not like things repel each other, but opposites attract. Now in that case, what we're looking for is, here's an empty orbital, here's an empty orbital. This empty orbital wants to be close or far away from these electrons in these bonds? Close. Where can it be as close as possible to those electrons in those bonds? Also sp2, because what's the bond angle from here to here? Because remember, this is trigonal planar. That's 90. Right? That bond angle is 90. So this empty orbital can be closer to these electrons, right, in all of these three bonds. In this case, does the bond angle from here to here, what's the bond angle from the empty sp3 orbital to the filled CH bond? What's that bond angle? Still 109.5, so that's farther away. So again, even that way, sp2 is still a better conformation. If I put a radical in there, if I put one electron, let's do that in black. Let's say if I do a CH3 dot, and I put one little electron in there, is that carbon electron rich or electron deficient, would you say? Does it have a full octet? No, right? This carbon up here still doesn't have a full octet. So is it electron rich or deficient? It's still deficient. So what argument makes the most sense? We want to get the deficient thing as closest to the electron density. Still want to spread them out, so it's still sp2. And now, here we go. Do the blue. But what if it was a carbanion? What if there is an extra pair of electrons? So I'm going to erase the little black dot. I think. Maybe I won't. I said I was lying. What if I made it 2 blue dots? Now, that orbital has 2 electrons in it. Now that orbital is filled. Now, where does it want to be? Now it wants to be sp3, right? So This wants to be sp3 because a filled orbital, again, wants to be as far away from these bonds as possible, right? While these two, this one's in, the carbocation is sp2, electron deficient, and the radical is also sp2 because it is electron deficient.
Will that be the same for nitrogen and oxygen if they're electron deficient? They're going to be the sp2?
Oh, excellent question. It does not work as well for oxygen and nitrogen. This is a carbon thing.
Okay.
Good question. So when carbon and oxygen or nitrogen and oxygen have plus charges, don't apply this to that just yet. Good question. This is just for carbon. Carbon, carbon, carbon. Organic chemistry. Carbon. So we're going to talk about some dipole moments. So one thing that's important to remember is you can have dipole moments refers to the whole molecule, right? Whole molecule. Right? Is the molecule itself have like a electron rich end and electron poor end, or is there like some sort of tug of war going on that's not evenly balanced out? Because you can have polar bonds in a non-polar molecule. I may have once argued this with a person very heatedly. I was right. But let's take for example, that exact example, this, carbon dioxide, right? CO2. Does it have polar bonds, polar covalent bonds? Yes. Right? This molecule has, right, polar CO bonds. But does the molecule itself have a dipole moment? No, because we're equally pulling these two directions. Incidentally, what's the hybridization state of this carbon? Why? That's right. Has 2 pi bonds, so it has to have 2 p orbitals. That's the hybrid state for sp. Very good. And the bond angle here is 180. So they're pulling literally in completely opposite directions, right? Cancels it out. Polar bonds, molecule doesn't have a dipole though. More interesting, we said, let's do a metal. What if I got some nickel here? This may bring some traumatic experience back from Gen Chem, but yeah, I'm doing it. Anybody remember what this geometry is?
No.
Not tetrahedral. Octahedral. All right. Octahedral. All right. Remember FAC and MER? Let's really think about how things are going to pull. Let's put a chlorine here, an H here, an H here, and a CH3 here, and a CH3 here. So does this molecule have a dipole moment? Yes. Where is the dipole moment at? It's almost coming straight out at us, right? So how would I draw it? I don't know. You'd say, there. You'd say, it's coming out. It's outward. Right? Right? So that's what we're looking for. Can you see where it's coming from, right? Octahedral is even more complex than we deal with. So maybe this will be even easier to see now. What if I showed you a carbon, right, in a tetrahedral geometry? Does this molecule have a dipole moment? Yes. Where's the dipole moment going towards? Kind of this way, right? Kind of going off that way.
Can you go over the difference between polarity and a dipole moment?
Sure. Polarity, polar bonds. Are you talking about polarity and polar bonds, or polarity just the term polarity?
Like a polar molecule versus a dipole moment.
A polar molecule is a molecule with a dipole moment.
Okay.
All polar molecules have dipole moment.
Okay, and a dipole moment is just like where the electrons are like more towards, go towards one side more often, right?
Right.
Okay.
So it can't be balanced out. So if you look for symmetry, right? So if you start seeing symmetry,
Yeah.
right? See how it's symmetric, this molecule's symmetrical, right? It's getting pulled equally in the same directions. Those molecules don't have dipole moments.
So if you were to switch the nickel one on H and a Cl, then that would have been.
Right, good question. So what if I had done, so, let's see if I can do that. It won't let me. So what if I took out, if I replace this Cl with an H, I replace that H with a Cl, now does that molecule have a dipole moment? No. Right? It's equally being pulled in those directions. The Lewis dot structure of HCO3. Work on that and we'll talk through it. Also, you want to make sure you include a negative right there. So let's talk through this. So one of the pieces of advice I gave people was something on the farthest left is usually in the center, unless it's a hydrogen, right? Because hydrogen can only have how many bonds? One. So putting that in the center doesn't make sense, right? So let's put carbon in the center. We'll put the O's around it, right? Usually if you have an H with these things, you usually want to put the H on the oxygen, usually not on the carbon for most of these things. So now here you are. So far so good. You need to have a negative charge. So as it stands right now, you have a negative charge on what? The oxygens both have negative charges. And the carbon has a negative or a plus charge? Plus. So right now, this isn't a wrong Lewis dot structure, but is it the best Lewis dot structure? Why not? Oxygen wants to have 2 bonds, but even a better reason. Carbon needs 4 bonds, which is a good reason too, but even better. Say it again. The octet rule, right? The first rule of Lewis dot structures, of course, is the octet rule, right? So if we can draw a resonance structure, right, where these electrons go down, where everybody has a full octet, we'd rather do that, right? Now, this isn't wrong, right? Does the charge balance out? Minus and a plus gets us to -1. It's not wrong. It's just not as good of a structure as this one. So now there's the other way to do it, where you actually calculate the lone pair electrons and really go through it.
Can you do that?
I can do that, right? So let's do that. Adding that all up. So hydrogen. So you got to figure out the valence electrons for all the atoms involved. So hydrogen has how many electrons? So you put a 1. Oh, so you put a 1 there. Carbon has how many valence electrons? 4. So put a 4 there. Oxygen has times 3. 18. Whoa, we can do that. Has a negative charge, so we have to add a extra electron for the negative charge. And that adds up to 24. 24. I can't count past 10 unless I take my socks off. All right, there's 24. Okay. So now we got to check to make sure, right? So let's check one of these structures to make sure we've used all the electrons, right? So the first thing we're going to do is let's draw in our lone pairs. This is good life advice. Always draw in your lone pairs. Write that down. Good life advice. Always draw in your lone pairs. So I've drawn all of my lone pairs in. So let's count these guys up, including the bonds, right? So all the electrons involved. So 2, 4, 6, 8, 10, 12, 14 for that one, 16 for that one, 18, 20, 22, 24. Good to go. And the charge is balanced. For one, because I know you want to. All right, so let's look at another one. Let's look at H2SO4. See if we can do this one. All right, let's take a look at this. So let's do the kind of the quick and dirty way, and then we'll go through the more of the method with the electrons, valence electrons way. So again, to the farthest to the left, there's hydrogen there. We want to put hydrogen in the middle. So what's the next thing farthest to the left? So let's put sulfur in the middle. And we all know sulfur is special because its position on the periodic table, it's lower than oxygen, so it's going down a column. And as you go down the column, what happens to the elements? They get bigger, and they may even be able to handle having more than 8 electrons around them, right? More than 8 electrons. So that might be going on here with sulfur, but we'll see. Put the oxygens there. Where do we want to put the H's? I say put on the oxygens, because have I shown you guys a lot of SH bonds, or you've seen a lot of S? Probably not. Nope. All right, so let's put them there. So let's put in some lone pairs, right? And you'll also look at the complex. Does the complex have a charge? No. But as I have it drawn here right now, these oxygens would be what charge? It'd be negative. Let's just draw it in. Let's test ourselves out here. So right now these would both be negative, right? That doesn't work, right? Our charge is 0. So the sulfur, let's just go through though. So what the charge really is here, right? Let's count our valence electrons. So hydrogen has how many valence electrons? 1, but there's 2 hydrogens, so it's 2. Sulfur has how many? 6. Oxygen has? Times 4. 24. 32. Right? 32 electrons total, right? How many electrons we need to have in the complex in lone pairs or in bonds? So let's add them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. But there's a problem here. So all here, but sulfur, right, is actually going to have a plus charge. So you could have drawn it this way. But sulfur would have to have a +2 in the situation, right? To make the charges balance out. Because where else could there be a charge? Right? These oxygens are happy they have 2 bonds. These oxygens are happy they have 2 bonds. These guys got negative charges. So the sulfur here has to be 2+, right? To make the charge make sense. So another way you could draw it is by just drawing in, instead of having the charges separated like that, you could draw them in as C dobondos. All right. Yes? Yes. Cool.